going to do worksheet 6 and 7. We're going to talk about parent functions and then transformations. Oh, man. Anybody want to pass out that blue worksheet in the back? That was supposed to be put out so everybody could get one. And I messed up. Otherwise, you can pick one up on the way out. But that's, yeah, you only get one. Share it with the class. All right, guys. It is a reference sheet, so please don't add anything to it. Okay? I will let you use it on the first couple quizzes on this stuff if you want. I'll have you lay it out on your desk, and if I walk by and you've added anything front or back and I see it, you will get a 0 on the quiz. So it's to be used as a reference sheet. It has parent functions. It has more than the basic ones we're going to do today. It even has trig functions on it. It's just a nice little reference sheet. All right. So today we're going to start talking about graphing transformations, describing transformations, writing equations for transformations, all this fun. So eventually you will have to do, take something like this, and I'm going to write this. And you're going to have to tell me that there was a vertical stretch by a factor of 2 and the graph was shifted vertically down 1. Okay? You're going to have to describe those. You may also have to graph it. You may give I may give you a graph and say describe what happened to the parent function or come up with the equation. Okay? All those kinds of things that are on here. All right. So a parent function is the simplest function in what we call a family. Okay, a group of functions that are very similar. Now, we're going to talk about the constant function today, the identity function, which is also just linear, the quadratic function, the cubic function, the square root, and reciprocal functions. We don't do reciprocal very often. Absolute value function, which you did a lot of in Algebra 2. Anybody remember this bad boy? This is called a step function. Its fancy name is the greatest integer function. I like this name better. It's called the round down function. Because if I told, and some books write it with double absolute values, our book was kind of a double brackety thing. But if this was negative 7.1, does anybody know what that would round down to? It has to round to the left, the next integer less than or equal to this. So it will round down to negative 8. Okay? If it was positive 5.9, it would still round down to 5. Okay? If it was 1/3, it would round down to 0. I like that name, the round down function, but the bottom line is we all hate graphing these. Okay? They feel uncomfortable. But are there a lot of things in the real world that your answer has to be a whole number? Okay, so there's a lot of functions that they use in real world math that eventually at the end they have to round to a whole number. So this is kind of that idea. The other thing is, like, if you go into the UPS store, they don't charge you another 5 cents for every ounce your package weighs, right? There's some kind of point where if it weighs over this, it jumps up to this price. And if it weighs over this, it jumps up to the next price. So a lot of things in the real world have to do with piecewise functions and even this greatest integer function. All right, so on the notes, we're just going to do a real quick sketch, okay? Constant function is some kind of a horizontal line. Identity function is the basic y equals 1x line. The quadratic function is your basic parabola at the vertex. Now, this is the parent function. It's not what all the it's not necessarily true of all the transformations. In other words, this cubic function, it says, is symmetric about the origin. and it looks like this, okay? If I slide that to the right one, is it symmetric about the origin anymore? No. Okay, so just so you know, it's the parent function that this is true of. Yes, it's not considered a vertex. It would like be an inflection point actually, because it changes from concave. Yes, but the parent function is symmetric about the origin. Okay, we're just gonna stick with that. The square root function looks like this, kind of. Right? Again, we start reflecting that over the y-axis, and it's not in the first quadrant anymore. Okay? So there are transformations that can occur that will change things. Reciprocal function looks like this. It has, you put in a positive, you get out a positive, so it has values in quadrant 1 and values in quadrant 3. Put in a negative, you get out a negative. We good so far? All right, absolute value function. I don't know if this is a good spot for you to put it in your notes or not, but somewhere, I just had students write, when you go to, if you want this on your calculator, you go to the math menu and then you arrow to the right once. Okay, and it's number 1 in that screen. I can show you. If I wanted to graph an absolute value function, I go to y equals. I go to math button, arrow to the right, and it's this ABS. Okay, so maybe we should write that there. That would be more helpful. It will say ABS. And then you'll take the absolute value of whatever's in the parentheses. Everybody okay? Where to find that? The greatest integer function, again, is this guy. Everything over to 1, less than 1 is 0. Starting at 1, it stays 1 until it gets to 2, and then it goes up 2. Okay. Those are really supposed to all be the same size. I don't know why mine look like they're getting longer as they go up. That's not a good plan. All right. This on the calculator is called INT. If you go to the math button and you arrow to the right, anybody find it? Is it number 4 maybe? 5? Okay, thank you. It's number 5 and it says INT, like greatest integer function. All right, and a cubed root function we will do in this class, and it looks like this. Actually, it looks pretty skinny, but that one's stretched, I guess. But it's the cubic graph rotated sideways to a cube root. The cube root is under math, and it just looks like this. And I think it's number 4. You don't have to arrow to the right for that one. Is it 4? You just go math. Okay. I don't know if that's a good spot for you to write them down, but do you at least think you could find them all now if you had to graph them? All right, so those are the parent functions. We're just going to spend 2 more minutes talking about parent functions because we're going to talk about reviewing all this fun vocabulary. So here's my first one, an absolute value graph. I want to know what the domain, range, intercepts, symmetry. I want to know if it's continuous, end behavior, and where it's increasing or decreasing. All right, everybody knows what the absolute value graph looks like? Okay, so what do you want to say about domain and range? Okay, domain is all real numbers. Range, Good job. Square bracket, 0 to infinity. Everybody good? Bottom to top. Intercepts? Well, it crosses the x at 0 and the y at 0, right? So I just write down 0, 0. Crosses both axes. Symmetry? Mine doesn't look symmetric around anything, but it's supposed to have symmetry with what? Y-axis, which makes it an even function, yes. It's weird because it doesn't have even exponents, right? But it is an even function. Continuous, any holes or breaks or asymptotes or anything? So this one, yes, it would be continuous. All right, end behavior. I'm going to practice by saying the function is going what? Okay, this is y. So up would be infinity. As x approaches, yeah, I'm going to do left side first. F of x approaches infinity also as x approaches positive infinity. Okay, I don't care if you'd use y instead of f of x. I don't care if you put the x approaches in front. I just want to know that if I put blanks on a quiz, you could do whatever notation I give you, right? Or however you want to do it. I will count it right. Any questions about end behavior? All right, do you remember increasing, decreasing? It's x intervals. Increasing would be where the function is going up. So what do we want to say for x values? The right side is increasing, so 0 to infinity. That's a really big comma, Hofbauer. Okay. And decreasing, x intervals from negative infinity to 0. And remember, increasing, decreasing, you never need a bracket. It's just a parenthesis. Same with concave up, concave down, which this graph is not, has no concavity. It's not a curve. All right, I'm going to give you 1 minute and 10 seconds. Can you do all of them for this one? Ten seconds. Domain and range. Yeah, all real numbers. Are we good? Intercept crosses x at 0 and y at 0. Symmetry. Okay, what do we write there? If it's an odd function, it has origin symmetry, yes. Yes, it is continuous. All right, anybody want to do end behavior? Good job, left end down. Yeah, that's supposed to be an infinity. Yeah, it's supposed to be, it's like a dead worm or something, I don't know. All right, so it's going up on the right. Increasing? Yes. And it's never decreasing, right? Concavity would change. I'm not going to write this, but what is this concavity and this concavity? To the left of 0, it's down, and to the right, it's up. Oh, you guys are good. Okay. Transformations. Going to the next part here. Transformations. There are two kinds the book talks about: rigid transformations and non-rigid. Rigid are transformations where it stays the same size and shape. So if you shift it left, right, up, down, stays the same size. If you flip it over, what do you think? Same size and shape. Okay? When does it not stay, or non-rigid transformations? Yep. Stretch it or shrink it, or take an absolute value. That's kind of a weird one. Okay. Vertical transformations are when you add something onto the back of the function. If it's a positive number, it goes up. If it's negative, it goes down. When you do something inside of the parentheses to the function, okay, that's a shift left or right, and it's always the opposite of what it seems. If you can simply remember that anything that happens inside the parenthesis is the opposite of what it seems, you'll be in good shape. Let me explain what I'm talking about here. If f of x is, for example, a parabola, okay, and I add f of x plus 2, that would slide it up 2, right? And it would change the y values. If I have f of x minus 4, it would slide it down 4. These are vertical translations. All right. But if I have the same function and I decide to do f of x plus 2 inside of here, what does that do? Instead of sliding it to the right 2, it slides it left 2. Well, it's like when you look at this notation, how it's always x minus h, it's the opposite. So when we put a positive 2 in there, it slid it to the, if I put a positive 2 in here, the graph actually, well, it says x minus 2, so it's to the right 2. Yes, yes. All right, so if we have x minus 4 with it all inside here, it shifts right 4. So is that changing x or y values if you're going left and right? X values, okay? And these are horizontal shifts. Those seem okay? All right, so what does this one do real quick? Takes that absolute value and does what? Up 4, left 3, 2 things. Yes, I would prefer you said in that order, like you're reading it from the inside out, okay? Right 2, down 1, but it's not wrong. The order isn't going to matter on that question. We're going to talk in a minute about when order does matter a lot. All right, what about this one? Takes your basic cubic graph and does what? Down 5. Left would be this, okay? So what's this one? Right 3. This one? Left 2, up 4. Are we good? All right. Now we're going to talk about reflections. All right. A parabola is not a good example for doing reflections, because what happens if I flip a parabola that opens up around the y-axis? Can you tell I even did it? Can't tell it, okay? So we're going to use a square root graph. If you put the square root of the negative on the outside, it flips across the x. If you put the negative on the inside, it flips across the y. And that's the general rule. Okay, so if we had a square root graph as our parent function and we did negative square root of x, that would reflect it over the x-axis. So this one would have been here, and it would now be here. Okay, it flips it upside down. Which changes x or y values. Okay, and negative on the inside. So if we had this parent function here and we did square root, oh, I made that look bad. Square root of negative x, it would reflect this way, because you could put in negative numbers, take their opposite, that would become positive, and then you could square root them. So it's reflected left to right over the y. So it changes x values. There are a lot of graphs that you can't tell. They already have y-axis symmetry, or they already had x-axis symmetry. You wouldn't know. Wouldn't be a function if it had x-axis, but that's okay. Everybody got what they want? Whoops, what'd I do? All right, the order is very important part of the time. I always think of it as if I were to put a number in here, I would subtract 1. Is everybody looking up here? Then I would take the opposite sign after I square rooted, and then I would add the 2. So that's the proper order to talk about this. You would say it's going to shift right 1, reflect over the x, and then shift up 2. Let's talk about that. So here was the graph. It reflected over the x and then shifted up 2. So it turned out up there. Okay? If you didn't do it in that order, you might come out with what this is saying, which actually, can you think what this is trying to tell you? Write 1, and then you're still in this parentheses, so you would go up 2, and then the negative on the outside would then reflect over the x. Let's think about that. Here's the original one, okay? If I went right 1 and up 2, now I'm here, yes? If I reflect that, it's down here. Reflect doesn't mean just flip it upside down from where it is. It means totally move it across the x. So do you understand that this and this aren't the same thing? Okay, so you have to describe those very carefully to me when you do those, and we'll talk more about that as we get to that kind of question. Then we're going to talk about dilations or shrinking and compressing. They do the worst example ever here, because parabolas, if you shrink them in, it looks like you stretch them up, right? Same difference. So I'm trying to give you an example here. If you had some weird function like this, I'm going to call this f of x. If you kept the same scale, this would be 2f of x, because do you see the zeros stayed the same? But it's stretching up twice as far and down twice as far. That was my attempt, okay? The blue would be 1/2 f of x, because the zeros stayed the same, but I only went up half as far and down half as far. Got it? This is different, okay? If I did, this is going to confuse you, f of 1/2 x. Remember what I said about inside the parentheses? What does it do? Opposite of what it seems, yes? So half on the inside doesn't shrink it, it stretches it horizontally. So if this used to cross over here at -2, now maybe it's crossing at -4. And if it's still going the same height, okay? But if it used to cross at 3, now it's at 6. twice as stretched away from the x. And this would be f of 2 inside here because that shrinks it half the size in towards the y-axis. Yes?
Oh, I could type
Opposite of that. All right, so let's write this in. It is expanded vertically, which is up and down, right? So it's going to take, and it's not going to change the x-intercepts, but a 2 will make it go twice as tall. So it is stretched up and down, which changes y values. Okay, so this is like 2f of x. A 1/3 f of x, where the number is less than 1, between 0 and 1, will compress the graph vertically or shrink the graph in towards the x-axis like that. If my original function looked like this, okay, a 2 here shrinks it in like this. And f of 2x shrinks, not stretches, graph in towards the y-axis. So an f of 1/2 x would do what? Yes, stretch the graph out away from the y-axis and change x values. Again, opposite of what it seems like inside the parenthesis. This time it's a reciprocal value. So if it shrinks it in by a factor of 2, they are all cut in half. If it stretches it out down here by a factor of 1/2, they're all doubled. The zeros are twice as far away from the x, or the y-axis. All right, last one, I think, transformations with absolute value. If you throw an absolute value on an entire function, it takes all the negative parts and flips them above and makes them positive. If you take an absolute value and put it inside on the x, this is the weirdest one of all, guys. It cuts off the negatives, and then it says whatever it had on the right, it's going to have on the left. It makes it symmetric to the y-axis. Wait till we do one of these on your graphing calculator. It's so fun. Okay, this is what happens. I'm going to draw the same sketch as they did, okay? If you have a graph like this, if this was f of x, when you put absolute value around the whole thing, it would look like this. Think about it. Anything you put in that used to come out negative will now come out positive. All right, this graph, this time I'm going to slide it over here a little bit. Okay, this time when you put anything in, it immediately becomes positive. So what happens is you cut off the left first, and then you make the graph have y-axis symmetry. And it changes x values. This is not something I'm going to give you something real crazy. We're going to do a matching exercise with this tomorrow, and they're kind of fun. Okay. All right. Quickly, this is the other worksheet. It says describe what happened and then graph them on the same axis. So it started out with, well, they used g of x. G of x was the square root of x. And then they did this. Okay. Anybody remember what an x inside, an opposite sign, I'm sorry, inside does? Yes, reflects across the y, okay? And then the minus 1 back here did what? Down 1, okay? That's what it says here, reflected at the y and then translated down 1 and then they graphed it. You could type it in your calculator if you wanted to. All right, so let us try these. What's the parent function? There's really 3 parts to this. It says describe, graph the parent function, and this. So what is the parent function for this first one? Just the absolute value graph, yes? Okay, so let's draw an absolute value graph. It would go through 1, 1, 2. Oh, that's not 1, 1. Love this graph paper. Okay, go through 2, 2, and 4, 4, negative 2, 2, negative 4, 4. There's the parent function. Okay, before we actually graph it, which yes, you could use your calculator, but what can you describe using the transformations? What happened here? What should happen?
Oh, wow.
Right, shift horizontally, left 4.
That's right.
No, you right, left 4, I'm good. And then what is this going to do? Is it a horizontal or vertical change if it's outside on the whole thing? It's a vertical stretch. If you put the 1/2 inside, you would describe it differently, even though it really wouldn't change what the picture looks like. It stinks, I know. It's a vertical stretch by a factor of, or shrink, not stretch. It's going to shrink it. By 1/2. It's like you're sitting on it, but what is that going to do? It's going to stretch it out, right? You're not going to notice the difference. So, yeah, it's not a good example of this, really. It's going to go down 4, so it's going to be here. No, it's not. Just kidding. Where's it going to be? Left 4. And then it's going to go up half as fast. So where it went up to 2, 2, if you went over 2, it's only going to go up to 1. Where it went over 2 boxes and up 2 boxes, it's going to go over 2 boxes and up 1. Each branch actually has a slope of 1/2 or negative 1/2. It's going up half as fast. Do you see right here how this went over 2 boxes and up 2 boxes? Now when it goes over 2 boxes, it goes up 1. Half. It's been shrunk by half. All right. What's the parent function here? F of x equals x squared. So it'd go through 0, 0. If you went over 2, it'd be up at 4. That's enough of a parabola for me. Anybody tell what 2 things are going to happen? Down 4. What's the first thing that's going to happen? That's a vertical shift. But first we should say this 2 is going to do what? It's on the whole thing, so it's going to be a vertical stretch by a factor of 2. It's going to go up twice as fast. These are not good examples because you can't tell if it's horizontal or vertical change, okay? So we're going to shift it down 4 to here. And then when it went over 2, instead of going up 2 boxes, it's going to go up 4 boxes. It's stretching twice as fast, which is actually here where it originally. We'll have some better examples of vertical versus horizontal changes eventually. All right, this is an easy one. 0, 0, 1, 1. Where would be the next nice square root? Yeah, square root of 4 is 2. So it looks like this. What does this graph do? Left 3, which is horizontal, and up 1, which is vertical. I'm not going to write all that. I'm just going to do it. Left 3, up 1. And every one of those points goes left 3 and up 1. So it looks like this. We good with that? Okay. This is another one. I'm not real happy with their examples sometimes. Absolute value graph 1, 1, 2, 2, 3, 3. Like this. But what words are we supposed to use to describe when the 2 is inside? Horizontal, but it's a reciprocal relationship, remember? So it's not stretched horizontally by a factor of 2, it's shrunk by 1/2. It's a reciprocal relationship. And then what's that negative going to do? Yes, reflect over the x-axis. All right, so it's going to go upside down, and it's going to shrink in horizontally by 1/2. That just means instead of going over 2 before it goes up 2, it's going to go over 1 and down 2. It's the same as if the 2 was on the outside. That's why I say I don't like these choices they're making, because with a parabola, you actually maybe could tell. But here, if I put -2 out in front of the absolute value, it's the same as putting the 2 inside. All right. Who's got this one? What words? Somebody got me? Good job. Left 2, then what? Before we do that, it is vertically stretch by 2. If the 2 isn't inside, it's not the opposite of what it seems. It's exactly what it seems. A 2 stretches it. And then we're going to go down 3. So what did we have? Left 2, which is to here. Down 3. And it's basically going up twice as fast. The actual slope of each branch would be 2 now. Or -2 if you're on the left branch. Last one, because we're going to skip number 6, this piecewise, and talk about this guy. A cubic goes through 0, 0, 1, 1, 2, 8. Is it 2, 8 off the top of the graph? Is that the very top? Okay. So there's some points on the original cubic graph. Oh yeah, that's the original. Okay, now what am I supposed to do to it? 2 things. Inside here, I'm going to shift it what? Left 1. And then does anybody remember what the absolute value is going to do to it? You are right. Yep, because it's on the whole thing. So it's going to take all these ordered pairs that used to be down here, and it's going to flip them up. So what's it going to look like? It's going to look like a parabola. Okay. Reflect values below x to above the x-axis. Nice job. You guys let me finish the notes even. Yes, I will. 1 second. This is the assignment, guys. It says right here we went over 6A, B, and 7, and so this is the practice you're supposed to do tonight. The bold ones, there's 4, 5, 6, 7, 8, 9, 10 problems. Okay? 1.5, the first assignment. What do you need?